Now that we know what logarithms are, we're going to explore properties of logarithms. We're going to look at inverse properties of logs, apply product, quotient, and power rules of logarithms. Then we'll use those properties to rewrite a logarithmic expression in expanded form or to write several terms in a single logarithm. And then lastly, we will apply the change of base formula. So we've seen inverse functions before, and we know based on our previous lesson that y is equal to b to the x and y is equal to the log to the base b of x, where b is greater than 0 and not equal to 1. We know those are inverse functions. And recall what inverse functions do. If the original function takes a value x to some output y, then the inverse function will take that value y and spit back the value x, right? So it's a way for us to get back to the original number we started with before applying this function f. So let's look at this with two examples. If we have y is equal to 2 to the x and y is equal to log to the base 2 of x, we know those are inverse functions. We see that in this specific example. For instance, if I input 5, 2 to the 5 is 32. So this takes an input of 5 and gives me an output value of 32. Well, in the inverse function, if I put in the log to the base 2 of 32, this means what is the exponent of 2 that gives me 32, and that is 5. So this inverse function took the input value of 32 and gave me 5. We'll look at this with another example, comparing y is equal to 10 to the x and y is equal to log x, which is just the common log. So let's say I input the value 2. 10 squared is 100. So this function takes an input of 2 and gives me 100. But then if I find log of 100, that means what is the power of 10 that gives me 100, and that is 2. So we see here that it takes the input of 100 and produces 2. And we talked about that before, right? The interchanging of the x and y components. Well, let me rewrite this in another way. Instead of saying log to the base 2 of 32, would you agree that this is the same thing as, instead of 32, I'm going to write 2 to the 5. Right, 2 to the 5 is 32. So we just found that log to the base 2 of 32 is 5. So notice that when my input has the same base as the log, my answer is just the exponent, right? Log to the base 2 of 2 to the 5 is just 5. I can also see that with the log of 100. I can rewrite 100 as 10 squared. Well, the common log has an understood base of 10. My input has a base of 10, and notice that I'm just getting 2, which is the exponent. Now here's another way. I don't want to blow your mind, but let's look at this. Instead of writing 2 to the 5 equals 32, what if I write it like this? 2 to the log base 2 of 32. Well, we just learned log base 2 of 32 is 5, right? So 2 to the log base 2 of 32 is really 2 to the 5, which is 32. Or 10 squared equals 100. I can rewrite that as, well, 10, but what was 2? 2 is the same thing as log 100. So 10 to the log of 100 is really the same thing as 10 squared, which is 100. All right, so this is where we see these inverse properties taking place. That when I have a function, apply its inverse, I get back to what I started with. And this is really based on the composition of logs. So we can state this official property. Let f of x equal b to the x, and g of x is equal to log to the base b of x. for b greater than 0 and b not equal to 1 and a real number x, it will follow that f composed with g of x is equal to f of g of x, which is equal to f of log to the base b of x, which will be equal to b to the log to the base b of x, right? We replace our input x with the function g, and we just get x. Likewise, g composed with f of x is equal to g of f of x, which is equal to g of b to the x. Now we input the function f into the function g in place of x, so that gives us log to the base b of b to the x, and that is x. So when the base of the argument and the base of the log are the same, we get just the exponent, x. And when the base of the exponential expression and the base of the logarithmic expression are the same, we get x. So let's just apply these properties to simplify some expressions. In my first example, I have log to the base 3 of 3 to the 4. Well, because the base of the log and the base of that exponential expression inside the log are the same, we will just get 4. If you need to think about it, simplify. What's 3 to the 4? That's 81. And what is the exponent of 3 that gives me 81? Well, that is going to be 4. There are times when you can't simplify, and I just really want you to understand the inverse properties. Log to the base 5 of 5 to the 3x. Well, that will just give me 3x, right? Because think about it like this. Log to the base 5 of 5 to the 3x. Remember our definition of log. It means 5 to what is going to give me 5 to the 3x? Well, that has to be 3x. The natural log of e to the 5t. Well, remember natural log is log to the base e of e to the 5t. So the base of the log and the base of the argument are the same. By the inverse properties, we will just get 5t. Log of 10 to the 3x minus 2. Well, the base of the log is understood to be 10. The base of the argument is 10. So by inverse properties, we get 3x minus 2. E to the natural log of 7 is just 7. Right, because natural log of 7 means what is the power of e that gives me 7? Now I'm going to raise e to that power, and that will just give me 7. 10 to the log 2 is just 2. E to the natural log of x minus 3 is just x minus 3. We will use these properties soon. We're going to apply them when we solve exponential and logarithmic equations. So it's really important to understand these inverse properties. So when you have an exponential expression, you apply the log with the same base, you're just going to get what is in the exponent. When you have a base and you raise it to a logarithmic expression that has the same base, you're just going to get the argument of the log. Now there are some restrictions I haven't explicitly stated here, but when we take the natural log of x minus 3, write a variable expression, we are assuming here that x minus 3 is greater than 0 because a logarithm is only defined for positive arguments.